Good evening, everyone. I welcome you all to the problem solving session of the NPTEL course on IC engines and gas turbines. I am Pradeev E. I am one of the TA for this course. So, today I have some problems from the previous year assignments, and then I also have some problems on Brayton cycle. So, the first question is stage pressure rise in centrifugal compressor is dash that of axial compressor more than, less than, equal, not above mentioned. So the stage pressure rise for centrifugal compressor is more than the axial compressor, whereas the flow rate of the centrifugal compressor is less than the axial compressor. So axial compressors can be used when we want less pressure ratio but high flow rate, and centrifugal compressor can be used when we want high pressure ratio but lower flow rate. Pressure change in one stage of a fan is a dash than the one stage of a compressor. So pressure change of a fan will be lower than the one stage of a compressor. Option is lower. C. Fluid flowing through a turbine first encounters dash blades, nozzle, diffuser, none of the above. So first, before hitting the turbine, the fluid will flow on a nozzle. Gas turbines are used in engines working on Erection cycle, Rankine cycle, Brayton cycle, Stirling cycle. So it is used in Brayton cycle. Centrifugal compressors are the choice when space not constrained for high pressure ratio. High stage pressure rise is required. Both A and B, none of the above. So the answer is both A and B. Which of the following is a power absorbing machine? Turbine, diffuser, pump, nozzle. So the power absorbing machine,
Pump, sir.
yeah, pump. Which of the following is a power producing machine? Compressor, diffuser, pump, or turbine?
Turbine, sir.
Turbine. So here pump and compressor uses power, and diffuser is doesn't produce or uses any power. Turbine produces power. Consider the following process. So PQRS, P is constant pressure heat addition, adiabatic expansion, adiabatic compression, constant pressure heat rejection. The correct sequence of these processes in Brayton cycle is so. What are the sequence of the Brayton cycle process?
The first adiabatic compression,
Hmm.
next concentrated heat addition,
Hmm.
and next constant pressure constant pressure. No, sir. Adiabatic expansion,
Hmm.
next constant pressure heat rejection.
Okay. So what is the sequence? So first is 1 to 2 is uh,
Adiabatic compression.
adiabatic compression, right? So R comes first, adiabatic compression, and second one is constant pressure heat addition. Constant pressure heat addition is P, and then again adiabatic
Adiabatic
expansion,
expansion.
that is Q, and then constant pressure heat rejection, that is S. RPQS. So RPQS is
Option D.
option D. Thermal efficiency of the cycle for a given heat input decreases with increase in network output, decreases with increase in amount of heat rejected, always remain constant, increases with increasing network output.
Sir, option D increases with increase in net work output.
Yeah, yes. I just close it. Okay, increase with increase because uh, efficiency, thermal efficiency is uh, work output by heat input. So this is constant, and now option A is decrease with increase in work output. No, these two have if this increase thermal efficiency also increases. So that is only D is right. Fourth one, which of the tenth one? Yeah. Which of the following is not a positive displacement machine?
Sir, I don't know
Reci-
about this.
Reciprocating compressor, two lobe compressor, Wankel engine, etc. So all first three are positive displacement. And axial compressor is not positive displacement. So that is right. Do you know what is positive displacement?
Not sure.
So uh, you know how a reciprocating compressor works, right? So there will be like a engine, like piston cylinder arrangement. So there will be valves, intake and exhaust. So every time for every cycle, this air comes in and it will be compressed and sent out. So these two valves will be like a one-way valve. So this valve, intake valve allows only air to come in, and the outlet valve allows only air to go out. So this will be like spring loaded on them. So now you just you have a constant you have some volume, and then you compress to positively to within the volume, and then you get the pressure rise. So these are called positive displacement. Whereas in case of centrifugal compressor or axial compressor, you uh, rotate the blade, and because of the centrifugal uh, force imparted in the or kinetic energy imparted in the gas, then later you convert back to pressure ratio or pressure energy, and then you increase the pressure of the fluid. So and in case of a, so if you in here, if you put a valve and keep compressing, somewhere it will break. Here either this line will break or this piston line will break or something will happen. Whereas in case of axial compressor or centrifugal compressor, you can close the outlet and then still keep running, but there will be some pressure rise in the outlet of the pump, but still it will be able to keep compressing, able to work. But here it is not the case. The pressure will keep on rising until something breaks.
Sir, what is Wankel engine, sir?
So Wankel engine is it's like a rotary engine. There will be that is kind of an internal combustion engine. So this lobe will keep rotating in an eccentric way, and so there will be inlet and outlet, inlet air, outlet air. So first it goes, air comes in when the Wankel rotates, this rotor rotates, and then at second stage, maybe say the it will come here. So here was the intake, intake is closed, and now it gets compressed here as this rotates. And similarly, there will be a spark plug here, and then expansion occurs at this region, and gas goes out. I'm not able to draw it properly, so if you see the image, we'll get to know.
Yes, sir, I think this type of
Yeah.
engine.
Okay. Intensive property of a system is one whose value does not depend on the mass or size of the system, like pressure, temperature, etc. It depends on the mass of the system. does not change when the system undergoes any process, belongs to system and surrounding both.
Sir, they belong to system and surrounding both.
No, no, no. Intensive property is like that the property that doesn't depend on the mass or size. So enthalpy, say volume is extensive property. You make it if you want to make it intensive, you can write it as specific volume divided by mass. Then it will become intensive. So this is also inverse of rho. So then temperature doesn't depend upon the mass of the system. Sorry, pressure and temperature doesn't depend upon the mass of the system. And you write specific enthalpy, which is the total enthalpy by the mass of the system. Then, so this is intensive, and this is capital H is extensive. Okay, are you able to follow?
Okay.
Work and heat are properties of system, path functions, point functions, properties of surrounding.
Sir, path function.
Yeah, path function. Why they are path function? So if you have a if you draw a process in the PVA diagram and you have some process going like this, where say from state 1 you move to state 2, undergoing some process. Now how do you calculate the work? You say work is PdV, integral PdV, and that will be the area under this curve, right? So now the 1 to 2 can also be went like this. Now you have this additional area, or you can also could have gone like this. Then you have lost this area in calculating the total work. So that is why we say uh, work is a path function, and same goes for the heat also. So for heat, if you draw in T yes diagram, same goes. So here also Q is integral TdS, and it depends upon the path that you follow. Which of the following example of open system? Compressor, turbine, heat exchanger, all of the above.
Turbine, sir.
And compressor,
The compressor also, but I don't know about heat exchanger. It is a closed system.
what is
Heat
the open
exchanger.
system? How do you
So
define open?
the air will not be reused. The flow.
That is with concern to some engine. Say gas turbine, open gas turbine or closed gas turbine is based on how you use working fluid back again or not. So this is like a thermodynamic system. You call it open or closed. So open system, the open thermodynamic system is where you have some mass transfer, heat transfer, work transfer. everything can happen. So this is open system. So we have other types like closed system and isolated system. So in closed system, there is no mass transfer, and there could be heat and work coming out or going in. So this is a closed system. Whereas an isolated system, mass transfer is zero, work is zero, heat transfer is zero, work transfer is zero, everything is zero. So this is an isolated system. So here, in case of a heat exchanger, so heat exchanger will have some two fluids coming in and going out, and so that means there is some mass transferring in and out, and similarly heat is also transferring in and out. So it is a open system. Same goes with the compressor and turbine. Fluid goes in and out, and work is also transferred either to the machine or the work is transferred from the machine to the server. So all of the above is the right. Have any questions?
So,
So next, the Brayton cycle with reheater is preferred over simple Brayton cycle because of higher network output, higher heat rejection, higher heat supply, higher compressor work.
higher network output.
Yeah. So after the first stage of the turbine, we again heat it back using a reheater, and then uh, extract more output from using a second turbine. So that means for a given mass of the fluid, we are able to take more work output in one cycle. So that is higher network output. Consider the following statements. In open cycle gas turbines, working fluid is always taken from the atmosphere at the inlet. In closed cycle gas turbine, working fluid is recirculated throughout the cycle. Brayton cycle is always suitable for aircraft. So which of the following statements are correct?
Sir, option D.
Okay, yeah. For all three statements are correct. In a gas turbine power plant, use of intercooler always decreases the expansion work, network output, compression work, heat supply.
So heat supplied.
Heat supply. What is an intercooler?
I don't know about that.
Okay. So intercooler is where you have first compressor and then you cool it and then you put another compressor. So instead of compressing in one stage, now you compress it two stages. So this 1, 2, 3, 4. To represent this in a PV diagram, if you have to compress, say from P1 to P4 with a we are using with a single stage, you would have gone somewhere like this 1 to 4. Now, if you are cooling, then you stop somewhere at point 2 and then take like you use a intercooler that is between 2 and 3 where the heat is rejected at a constant pressure. So that means at constant pressure you reject heat, that means the volume comes down, and now you again compress from 3 to 4. So now you have come to the same. So this is 4 and maybe that is 4 dash. Now you have reached the same pressure level, but if you calculate the work you have done, you would be ending up with a lesser work input. So in terms of here you have to take work as integral VdP for flow process. So now you will take only this work, this area as a work that is done by work done to the compressor to compress the fluid. Whereas if you have to compress in a single stage, you also would have you have to do work on this area also, the black hatched area. So now you get some advantage of reducing the compression work. So that is the advantage of having an intercooler. Work ratio in gas turbine power plant is defined as the ratio of net work output to turbine work, compressor work to turbine work to compressor work, none of this.
Turbine work to compressor work.
Actually it is net work output to turbine work. Network output is turbine work minus compressor work. So this ratio is work ratio network is WT minus WC by using regenerator in a gas turbine power plant decreases net output and increases thermal efficiency, decreases both thermal efficiency and net output, always increases specific work output, always increases thermal efficiency and decrease heat supplied.
Sir, option A decreases net output and increases thermal efficiency.
No, no, no. See, if you decrease output, however, thermal efficiency will increase. So, do you know what is a regenerator in that gas turbine power plant?
Yes, it will regenerate the air from the turbine and it will reduce the heat.
We use the heat, right?
Yes, sir.
So it comes here. So there will be some regenerator, and then there will be a combustion chamber, and then it goes to a turbine, and then from here it goes to this regenerator. So because of this, now you need not supply the same heat energy that you have supplied earlier. So had this was not there, if this was not there, you have to supply the this say this is T3 and this is T2. T3 minus T2 has to be supplied by the combustion chamber. So now what happened? You have heated it to some temperature like T uh, 2 dash. So now T2 dash is greater than T2 because you are using the output heat energy from the exhaust from the turbine. So now you will end up with T2 T3 minus T2 dash. Say for example T3 was say 1000 Kelvin and T2 dash just after compressor it was only 400 Kelvin. But now sorry T2 after the compressor. And now because of regeneration you are able to increase this by say 500 Kelvin. Right. So without regeneration you have to supply Q in should be MCP into T3 minus T2, that is 1000 minus 400, right? So this is 600. Now with regeneration Q in is MCP 1000 minus 500. So only 500 you have to supply MCP into 100. Earlier you have supplied MCP into 600. So that means you are reducing the heat that you are supplying using combustion chamber, because combustion chamber is where you put the actual fuel and then increase the temperature of the working fluid. So this is always increases thermal efficiency and decrease heat supply. In gas turbine power plant, effectiveness of heat exchanger is defined by the ratio of actual heat transfer by maximum possible heat transfer, heat rejection by hot fluid, by heat gain by cold fluid, heat gain by cold fluid by heat rejection by hot fluid, maximum possible heat transfer by actual heat transfer. So this is a general heat exchanger definition. So this is the heat exchanger that we are using. So the effectiveness of the heat exchanger is actual heat by actual heat transfer by maximum heat transfer possible. So actual heat transfer is uh, H5 minus H6 by maximum heat transfer is when this H6 has become the temperature of the 2. So that is H5 minus H2. Say here it is 400 Kelvin, and after heating it has got say 500 Kelvin. And here at the outlet it is say after the turbine it is from 800 Kelvin. It has come to at the 6th it has become say 450 Kelvin. So in practical cases, only when there is a difference in heat temperature, there will be some heat transfer, right? So it has to be the heat is the transfer from the 5-6 stream, that is the exhaust stream, to the inlet air stream. So the exhaust stream has to be at a high temperature, say 450 Kelvin. Only then it can transfer the heat to a 400 Kelvin stream. Now assume that it has become assume that it has become 450, this at 6th it has become 400, then that is the maximum that you can transfer. Beyond that, from the hot fluid you cannot transfer to the cold fluid, right? So that is the maximum heat transfer is on the denominator. From H5 it has become to the H2, enthalpy at state 2, and on the actual one is only H5 to H6. So this is actually transfer by maximum possible heat transfer. Do you have any questions in this?
No, sir.
Okay, there are no questions. We can go to the next one. In a gas turbine power plant, compressor work is 500 kJ per kilogram. The heat supplied is 1 megajoule per kilogram, and the turbine work is 800 kilojoule per kilogram. The thermal efficiency of the plant is, how can we find? So the compressor work WC is given as 500 kilojoules per kilogram. Heat supplied is 1 megajoule, that is 1000 kilojoule per kilogram, and turbine work output is 800 kilojoule per kilogram. What is the efficiency? Efficiency we know. Can you try to answer this? What is efficiency? You can either unmute and answer, or you can also type in the chat box.
For 30%.
30%, okay. How do you say what is efficiency first?
Sir, work done by turbine minus work done by compressor
Hmm.
divided by heat supplied.
Okay, and that is 800 minus 500. 5,000. So basically efficiency is output by input. For a power plant, the output is the work done and the input is the heat supply. So work done, we get some work from turbine, but we are spending some work to the compressor, so we have to take the subtraction of it, network output of it. Eighth one, optimum compression ratio. This is actually pressure ratio. Optimum pressure ratio for maximum specific output for ideal gas air turbine plant operating at initial temperature of 290 Kelvin and maximum temperature of 1000 Kelvin is close to 1595 or 6.
So what we need to find there?
We need to find what is which of this pressure ratio will give me maximum specific output. Any idea?
No, sir.
So assume the question was like which of the following will give me the maximum efficiency. Then what would be the answer? How do we calculate the efficiency of a Brayton cycle? We have some formula, right? Efficiency of Otto cycle. So efficiency of Otto cycle is 1 minus 1 by compression ratio power gamma minus 1, right? And for Brayton cycle it is 1 minus 1 by pressure ratio power gamma minus 1 by gamma. Both these are almost same. How is like if you convert this to temperature ratio, both will be like 1 minus 1 by T2 by T1. So 1 minus 1 by the T2 by T1 is a temperature before compression and temperature after compression. So now, so if they have asked for the maximum efficiency, we can directly say that the highest pressure ratio is going to give me the maximum efficiency. So that will be 15. 15 pressure ratio of 15 will give me maximum efficiency. But now we are asked for the highest specific output. So highest specific output means work done in a cycle, right? So that is Wt minus Wc. And how can we write it in other ways? Here it is given that T1 is 290 Kelvin, T3 is say 1000 Kelvin, and we need to find which one will give me the maximum work done. So work done in case in terms of kilojoule per kilogram. So we can write efficiency. Efficiency is work done divided by Q in, and so from this work done will be efficiency into Q in. Now the T3 is the temperature at the end of combustion, uh, end of constant pressure heat addition. So that will have an influence on the Q in. So that is why, and efficiency will have an influence. Pressure ratio will have influence on the Q in. Sorry, pressure ratio will affect the efficiency, and T3 will affect the uh, energy that can be supplied. So both of this will combinedly will have an effect on the work done or the specific work output. So one simple way is to, like, we know what are the efficiencies. So what are the efficiencies? So, sorry, what are the pressure ratios given? PR is say 15, 9, 6 and 5, I think. 15, 9, 5 and 6. So for all this we can individually keep on calculating and find what is which one is giving the maximum work output. And there we can also solve this analytically. So first I will go with a simple way. I will just put pressure ratio and find, and we will see how to find the which one gives me maximum pressure, maximum specific output. So for pressure ratio is equal to 15, I can calculate efficiency is 1 minus 1 by pressure ratio power gamma minus 1 by gamma. So that is 1 minus 1 by 15 power 0.4 by 1.4. What is this? Efficiency. So I will write this efficiency 15.
So 0.53.
0.53. Yeah. So now I need to find Q in. So how can you find Q in? Q in is Cp into delta T. Delta T is T3 minus T2. So I hope you are able to remember what is 2 and 3 now. So we compress for a Brayton cycle, and then this is 1, 2, 3, 4. So T3 will be having the most highest temperature, and that is given as 1000 Kelvin. So this is given as 1000 Kelvin, and at state 1 is given as 290 Kelvin. Okay, so now if you draw in a TS diagram, first there will be isentropic heat compression, and then constant pressure heat addition, then expansion at isentropic condition, and then heat rejection. So now higher pressure ratio means that T2 will be higher. Pressure ratio high implies T2 also goes high. If T2 goes high, then this is already limited to 1000 Kelvin. T3 is limited to 1000 Kelvin. Then I will have only less Q in that is possible, right? Are you able to follow me? If pressure
Yes,
ratio
sir.
goes high, yeah. If pressure ratio goes high, T2 will go high. Then Q in will be limited. Q in will go down. But if pressure ratio is higher, efficiency will be higher. That is what we have seen from the relation 1 minus 1 by pressure ratio power gamma minus 1 by gamma. So there is a balance between these two. Now my work done is efficiency into Qin. So higher pressure ratio will give me higher efficiency but lower Qin. So there is a balance. At some point there is a balance. So that will give me the maximum work done. That is what we need to find. So for pressure ratio 15, we can calculate the value of T3. So how do I calculate T3? So T2 by T1 is pressure ratio power gamma minus 1 by gamma. That is 15 power 0.4 by 1.4, and T2 is equal to 290 into all this 15 power zero point 0.4 by 1.4. Can you calculate T2? So I would write this as T2 at 15.
Sir, 608.67.
628.
28 point,
Okay.
point 67.
6, okay. Uh, both of you have got the same value.
Yes, sir.
So next is Q in. Q in is MCP. Sorry, this is we are having in specific terms. We write only CP into T3 minus T2, and CP is known as 1.005, and T3 is 1000 Kelvin given in the problem, and T3 is what we just found. That is 328.7 Kelvin. Can you calculate Q in? So this is Q in for pressure ratio 15.
Sir, it's 373.18.
373.18 kilojoule per kilogram. Now if you want to calculate work done for 15, we have efficiency at 15 and Q in for 15. Efficiency is 0.53 into Q in is 373.18. Can you calculate work done?
Sir, 197.78.
197.78 kilojoule per kilogram. So this is a specific work output for when the pressure ratio is 15, and similarly we need to calculate for the other values. So we can say write a table pressure ratio 15, 9, 6 and 5, and then for each of this we will have a efficiency, we will have a T2. So with the T2 we can calculate Q in, and with Q in we can calculate out, right? So for 15 we have just found that is this is 0.53 efficiency, T2 is 628.7, Q in is 373.18, and finally work done is 197.78. So can you calculate the efficiency for pressure ratio 9? I'm just writing the values so that you can calculate easily. T2 is T1 into pressure ratio power gamma minus 1 by gamma, and Q is Cp into T3 minus T2. Yes, T2 is, sorry, T3 is 1000 Kelvin. And you have found the efficiency for pressure ratio 9.
Sir, 0.467.
Okay, 0.467. T2,
Sir, by 43.29.
Sorry, 500 and
43.
43.29. Q in
Sir, Q in is 458.99.
8.99. Okay. What time?
Sir, work done is 214.34.
Okay. Can we calculate the efficiency for 6 when the pressure ratio is 6?
So efficiency is for 6 is 0.4.
0.4. Okay.
Sir, 483.86.
483.86.
So Q in is 518.72.
118.72. Okay.
So and the work done is 207.48.
207.48. So now, can you guess, like, if you have a pressure ratio of 5, it is going to be more than any of these value, or it is going to be less than these values?
So less than.
Why? Less than is correct, but how did you say that? So here from 9 to 6 we saw that efficiency has dropped a lot, and even though this has increased, Qin has increased, we couldn't increase the work done, so that is reduced, right? And similarly, if you go to 5, this value will be further lower than 201. Okay, and if you go from 9 to 15, we see that this has decreased work done. So we have already reached the optimal value. That is 214 is the output, and that is at power pressure ratio of 9. If you plot this one, we have pressure ratio and sorry, we have work done on the y-axis and pressure ratio on the x-axis. So at some point 9 we got the maximum, and at 15 it is lesser, 9 it is higher, and then 6 it is lower, and 5 will also be still lower. So the curve will be something like this. We do not know, the maximum can be somewhere just next to it. It may not be exactly 9 because we have just saw 9 and 15, right? This is 6 and 5. So, but out of the given options, we know that 9 is sure for sure, and 9 is the right answer. But is there any other way to solve this problem? So we see, if we draw a graph between work done and the pressure ratio, we end up a curve like this, which is concave, convex upward. And if you want to find this maximum value and the point at which maximum occurs, is there some other way you would have come across in mathematics? Say this is y is a function of x. Now if you want to find the optimal, you find dy by dx should be should be 0. Dy by dx is slope, right? So at the optimal point the slope is 0. So here the slope is positive, here the slope is negative at this point, but at the optimal point the slope is 0. So if you able to get an expression for the y as a function of x, and then you differentiate it and equal to 0, then you will be able to find the value of y and x here when it is 0. So that will be the uh, uh, local optima, local maximum or minimum. So in this case, then to find if it is really maximum or minimum, then you should put a second differential, and then if it is greater than 0 or less than 0, based on that you will get it is, so greater than 0 is minimal, and less than 0 is maximum. How that this is like in this case it is maxima, so that means the rate of change of the slope itself is initially increasing and then decreasing, right? So at this point the rate of change of slope is decreasing, so from positive it has become negative, so that means the rate of change of slope is negative, it is decreasing, so that is a maximum. In case of a minima, the curve would be something like this. At this point the slope is 0, here the slope is positive, and here the slope is negative. So at this point the rate of change of slope is positive. So here we will get d square y by dx square is greater than 0, that means minimum value. Am I making sense, or is it too confusing? Or if you are not able to follow these, at least this one you are able to follow. Like if you find the slope and if it is 0, that means it is at the maximum value. Are you able to follow this?
Yes, sir.
Yeah. Okay. Now we can make an expression for the work done as a function of pressure ratio and then try to solve this, and that will be much easier, and you will be like within 4 or 5 lines of derivation we'll be able to solve this. So the other person also able to follow. Jayanta. So now here efficiency we know that it is 1 minus 1 by pressure ratio power gamma minus 1 by gamma. So now I will be having many times gamma minus 1 by gamma, so I take alpha as gamma minus 1 by gamma. So this is 1 minus 1 by pressure ratio power alpha, right? Efficiency. So I've got the expression for efficiency. Now I need to calculate Q in. Q in I know that it is Cp into T 3 minus T2. Here T3 is a given term. I need to find T2 as a function of pressure ratio. So I know T2 by T1 is pressure ratio power gamma minus 1 by gamma. So I take T2 as T1 into pressure ratio power gamma minus 1 gamma is already alpha. So now I can calculate substitute the T1 value in Q in, that is Cp into T3 minus T1 into pressure ratio power alpha. If I put work done is efficiency into Qn. Efficiency is 1 minus pressure. So this I can write it as 1 minus pressure ratio power minus alpha. So I write pressure 1 minus pressure ratio power minus alpha. So this is efficiency. This term is efficiency. And now I have Qn. Qn is Cp into T3 minus T1 into pressure ratio power alpha. This is Qn. Are you able to follow this?
Yes, sir.
Yeah.
Yes, sir.
So now we have written work done as a function of pressure ratio. Here Cp is constant, T3 is constant, that is given in the problem as 1000 Kelvin. T1 is also constant, that is given again in the problem as 290 Kelvin. So here the only variable is PR, pressure ratio. Alpha is again gamma minus 1 by gamma, that is also a constant. Now we can differentiate this and sorry.
So it will be on seventh page, seventh or eighth.
Yeah, I got it. I think it's on 9th page. I think somewhere it is interchanged. 11th page should have come earlier. But anyway, while uploading, I will change it. So we have got this expression for work done. So let's rewrite this. Now I need to differentiate this work done with respect to pressure ratio and equate to 0. Then I will get the maximum value of work done. So for this, I need to calculate this one. Partial differentiate is with respect to work done with respect to pressure ratio. So I can write this into individual terms. So I would have Cp. First, I would write work done is equal to Cp into this is so first 1 into the right hand side terms, that is T3 minus T1 into pressure ratio power alpha, and next minus PR into the other terms, that is minus PR minus T3 into PR power minus alpha, then minus into minus plus I will have, then T1 into pressure ratio power. Here I had minus alpha and right hand side I had alpha. So then it will get nullified, right? So there is alpha minus alpha, that is 0. So this will be 1. So I will have only T1 left. So this is for that. Now I need to differentiate this work done with respect to pressure ratio, and then yeah, first I will do that. So here I will have Cp as constant, it will be there, and T3 and T1 are constant, so it will go off. So here essentially like I can multiply every term with Cp and then find out and then take the Cp common. So T2, T3 and T1 are constant, so it will go off. I will be left with, I can take say negative outside, so then I would have T1 into alpha into pressure ratio power alpha minus 1 and plus T3 into alpha into pressure, or here it will be minus alpha into pressure ratio power minus alpha minus 1. Now if I want to equate this to 0, 0 is equal to I would rewrite this minus Cp into T1 alpha PR power minus alpha plus T3 minus alpha PR power minus alpha minus 1. So here this will go off. Now I will be left with T1 into pressure ratio power alpha is equal to T3 into so I would have alpha also here. Here also I will have alpha pressure ratio power minus alpha minus 1. So I think here also I had minus 1. Yeah, here it is minus alpha minus 1. So this is alpha minus 1. This is alpha minus 1. So alpha will get cancelled, and if I take T3 by T1 on the right hand side and all the pressure ratio terms on the left hand side, I will be left with this will be alpha minus 1, and when that right hand term comes to left hand side, I will have plus alpha plus 1. So plus 1 minus 1 will get cancelled. I will be left with pressure ratio power 2 alpha is equal to T3 by T1. Now pressure ratio is equal to T3 by T1 power 1 by 2 alpha. Now we can calculate what is alpha. Alpha is gamma minus 1 by gamma, right? So what is alpha? 0.4 by 1.4. Can you calculate the value of alpha?
Sir, so I find the PR value, sir. It's 8.72.
PR is equal to
72
8.72. Okay,
7257.
57. So this is 257. Yeah, you're right. So now T3 T1 we know 1000 and 290s, and substituting all we will get pressure ratio of this. So now we have exactly find the pressure ratio that will give me the maximum specific work output. Earlier we were only just putting by trial and error for different 4 values that was given in the options, and now we have got the actual value. No, that is 8.72. Now if you see within the options, that is the closest match we'll get. Among 15956, 8.7 2. So 9 is the best option. So in some question, if the options are not given and you are asked to find and enter the values, type the values, then you have to follow only this method. You cannot, by trial and error, you can again keep on going, but there will be so many iterations that you lose time doing that. So the best is to put an expression, find the maximum using algebra, and then. Do you have any questions?
No, sir.
Okay, we can go to the next problem. In an open cycle gas turbine plant, air enters the compressor at 1 bar and 290 Kelvin. The pressure at the exit of compressor is 5 bar. The isentropic efficiencies of turbine and the compressor are 90% and 85% respectively. Air fuel ratio is 60:1. Calorific value of the fuel used is 42 megajoule per kilogram, and mass flow rate of air is 2 kg per second. Assume air as an ideal gas with specific heat at constant pressure equal to 1.005 kilojoule per kg Kelvin and specific heat ratio as 1.4. Consider specific heat at constant pressure for fuel also as 1.005 kilojoule per kg Kelvin and specific heat ratio as 1.4. Find the following. So we have to find what is the heat supplied by fuel to the plant. How can we find this? Air fuel ratio is given, flow rate of air is given, calorific value is given. How do we find the heat supplied by fuel? Please unmute and answer, like either you know or you do not know, you can tell me.
No, sir.
No. Okay. The other person. Okay. Q in is mass flow rate of fuel into calorific value, right? Calorific value is given, mass flow rate of fuel has to be found out. So how do you find mass flow rate? Air fuel ratio is given, that is m dot a by m dot f. Here we know m dot a air fuel ratio, so m dot f can be calculated. M dot f is mass flow rate of air divided by air fuel ratio, that is 2 by 60. That is m dot f. And q in is m dot f into calorific value, that is 2 by 60. This is in kilogram per second into calorific value. So we will have calorific value in terms of kilojoule per kilogram. So that will be 42,000 kilojoule. So what is q in?
Some, sir, MF is 0.03, sir.
Okay. What is q in?
1400.
1400 units.
No, sir.
Say this is in kilogram per second and this is in kilojoules per kilogram, right? So finally we will get q kilojoules per second. So that is asking question, and that is we found the answer also 1400. Do you have any questions?
Yes, sir.
Next one, what is the work required to drive the compressor in kilowatt? How can you find this compressor work? The exit pressure of compressor is given as 5 bar. So we can calculate it. So T2 by T1 is equal to P1 by P2 power gamma minus 1 by gamma. So that is T2 is equal to T1 into P1 by P2 power gamma minus 1 by gamma. T2 is T1. So T1 is 290 Kelvin, and P1 and P2 are 1 bar and sorry, I think this is P2 by P1. So we have P2 is 5 by 1, 5 bar and 1 bar. This is gamma is 0.4, so this is 0.4 by 1.4. What is T2?
So 459.30.
3 Kelvin. Okay. Now compressor work is Cp into T2 minus T1. So that is 1.005 into T2 is 459.3 minus 290. What is compressor work?
So 170.14.
170.14. What is the unit? Kilojoule per kilogram, because Cp is kilojoule per kilogram Kelvin. We didn't use mass so far, so it is still in kilojoule per kilogram. So now to calculate the rate of work, we need to multiply with the air flow rate. So air flow rate is 2 kilogram per second into 170.14 is compressor. What is compressor work?
The 314.28.
340.28 kilojoule per kilogram. Sorry, kilojoule per second. Now, so this is the ideal work, isentropic work, but we were given an isentropic efficiency. For the isentropic efficiency of the turbine and compressor is 90 and 85%. So for compressor it is compressor efficiency is 0.85. Now, now this compressor efficiency can be written as work actual work. Sorry, ideal work by actual work. Why? Ideal compressor needs less work input, but actual compressor needs more work input. So efficiency is the other way. So now we have to calculate actual work of the compressor. W dot C actual is W dot C ideal by compressor efficiency. So this is 340.28 and compressor efficiency is 0.85. Can you calculate the actual compressor work?
Sir, 400.33.
400.33. Unit is kilojoule per second, that is kilowatt. So option A is right. Do you have any questions?
No, sir.
Okay. Next one, actual turbine outlet temperature in Kelvin. How do we find? So that would be same PV diagram. We had compression 1, 2, 3, 4. Turbine temperature outlet is T4, right? T4 is what we need to find. We know T1. T1 is 290 Kelvin, and we know P2 by P1. I think we also calculated T2, right? T2 is 459.3. T2 is 459.3 Kelvin, and we know the pressure differences, like between 3 and 4. It is here. It is 5 bar, and here it is 3 bar. Sorry, 1 bar. So using pressure ratio, if we have temperature at state 3, we can calculate the temperature at state 4. So how do we calculate the temperature at state 3 after combustion? So we know Q in dot is mCp delta T. So delta T is, we have m dot. So here it is, after combustion it is both fuel and air that is coming into picture. So we will have m total m, that is mt, into Cp into temperature differences between T3 and T2. Now we can calculate T3. That would be T3 minus T2 will be Q dot in by m dot total into Cp, and this is T3 minus T2. Now T3 is equal to T2 plus Q dot in divided by m dot total into Cp. So m total is mass of air plus mass of fuel, right? So T2 is 459.3, and Q in is we just found earlier, right? 1400 kilojoule per second. So this is 1400 kilojoule per second, and on the denominator we have m dot t. M dot t is m dot t is m dot a plus m dot fuel, and m dot a we know it is 20, and for m dot f from air fuel ratio we found that it is 2 by 60, and so this is 2 plus 2 by 60 is 0.03. 0.03, so this is 2.03. So we can roughly take it as 2 kilograms per second, because the effect of fuel is very less, because it is only 1/60th of the mass of air. And we have 2, and then for Cp we have 1.005. On numerator also we have kilojoule, and denominator also we have kilojoule, so it will be balanced. Can you calculate the value of T3?
So 1162.8.
1162.8 Kelvin. Now, using expansion, isentropic expansion, we can calculate the value at T4. T4 ideal, because there is an inefficiency of the turbine, which will say that the temperature reached at 4 will be different than the ideal case. Now, T4 by T3 is equal to P4 by P3 power gamma minus 1 by gamma, and T4 is equal to T3 into, so P4 by P3 is also P4 by P3 is P1 by P2. T3 is 1162.8. I write this as T4 ideal, 0.8, and this is 1 by 5 power 0.4 by 1.4. Can you calculate T4 ideal?
So 734.17.
734.1. Now, what is turbine efficiency?
So work done by turbine minus work done by compressor divided by work done by turbine.
No, this is for the entire gas turbine we are telling. So, I am asking only the isentropic efficiency of the turbine.
So the ratio of actual work output of the turbine and to the net input energy supplied in the form of fuel.
No. This is isentropic efficiency of the turbine, that is actual work by ideal work output. So, um, if you draw in TS diagram, we have two pressure ratios, and if you, in case of actual, in case of isentropic expansion in turbine from 1 to 2, we would have a straight line like this 1 to 2, right? But so this is called as 2s, that is in isentropic expansion s is 0, delta s is 0, but in actual we will have some increase in entropy. We will end up somewhere here, that is 2. This is pressure 1, this is pressure 2, right? So if you have taken the if you have gone isentropically, we will have H1, the enthalpy change is delta H, or work output is Cp into T, or okay, I will write this enthalpy 1 minus enthalpy 2s, or this is Cp into T1 minus T2s. This is ideal, but in actual I have only H1 minus H2, that is Cp into T1 minus T2. So here we can see T2 is greater than T2s. Since I generated entropy, I couldn't the temperature couldn't drop as in T2s for the same pressure P2. So this difference in actual and ideal case of the turbine, like how we deviate from the isentropic process, is given by the isentropic efficiency, eta T. This is different from the Brayton cycle efficiency that we have been. Are you able to follow?
Yes, sir.
So now we have found this ideal temperature, and that is so in our case this will be between T3 minus T4 by T3 minus T4s. So we have just calculated T4s. So this is 0.9 given in the problem. and T3 is 1162.8. T4 is, we have just calculated it as 734.17, and T4 is on the numerator. So now we can calculate T4. T4 will be 1162.8 minus 0.9 into 1162.8 minus 731.17. Sorry, 734.17. Can you calculate T4?
The 777.033.
777.0. This is correct.
Sir, it's 774.
774. Efficiency is correct, or okay. So this is 777 or 774, but in the problem, the closest one we have is 792. Do you have any questions?
Yes, sir.
Okay. Next one, thermal efficiency of the plant. How can you calculate? So thermal efficiency is, so this is the work, turbine work minus compressor work divided by Qn. We have already calculated Qn, and compressor turbine work, we, okay, compressor work is here. We just have to calculate the turbine work output, and then we can substitute everything in the formula. So for the turbine work, we have Cp into T3 minus T4. This is m dot A Cp into T3 minus T4 actually. So m is 2, which is 1.005, into T3 is 1162.8, minus T4 is 770. I would take average of these two values, that is 775.5. Can calculate turbine work output.
So 778.47.
This is kilojoule per second. So now the efficiency of turbine is 778.47 minus compressor work. So compressor work is 400, and heat input is 1400. Can you calculate efficiency?
Sir, 0.27.
0.27. So 29% is the closest to that. Do you have any questions?
No, sir.
Then I can move to the next problem. Air enters the compressor of a regenerative gas turbine engine at 300 Kelvin and 100 kilopascal, where it is compressed to 800 kilopascal and 580 Kelvin. The regenerator has an effectiveness of 72%, and the air enters the turbine at 1200 Kelvin. For the turbine efficiency of 86%, determine the amount of heat transfer in the regenerator. Next, the thermal efficiency, and assume variable specific heats for air. So variable specific means we need to have the table and then solve the problem. But for now, I think we will solve without the table, like assuming constant specific. So with the regenerator, so this is 2, 3, 4, 5 and finally 6. So this is the heat exchanger. Now T1, T2 is given, P1, P2 is also given. We can keep solving for at different states. So T1 is 300 Kelvin, T1 is 100 kilopascal, T2 is 800, sorry, 580 Kelvin, and P2 is 800 kilopascal. Air enters the turbine at 1200 Kelvin, so that means T4 is 1200 Kelvin, and the turbine efficiency is 86.86. The amount of heat transfer to this has to be found. So the effectiveness of the regenerator is given as 0.72. Can we solve? So here we know T3. Okay, T3 is not known. So if we find T3, then we can calculate the amount transferred to the regenerator, right? So this formula is this effectiveness can be defined as the actual heat transfer by maximum heat transfer. So effectiveness can be written as actual heat transfer is H5 minus H6, but maximum is H5 minus H2. this can be written in terms of temperature. T5 minus T6 is T5 minus T2. So this ratio is 0.72. Now we know the T4 is 1200 Kelvin, and we know the pressure ratios, that is 100 and 800 kilopascals. So based on these two, we can be able to find the isentropic T5s. So T5s by T4 is equal to P5 by P4 whole power gamma minus 1 by gamma. So T5s is T4 into P5 by P4 gamma minus 1 by gamma. So that is T5s is T4 is given as 1200 Kelvin, and P5 by P4 is P5 is at lower pressure, that is 100 kilopascal, by P4 is same as the P2 pressure, that is 800 kilopascal. Power gamma minus 1 by gamma is 0.4 by 1.4. Can you calculate T5 is?
So 662.45.
62.45 Kelvin. Now this is the isentropic temperature. Now actual can be found out. So actual for this we have turbine efficiency of 0.86, and say this 0.86 is given as T4 minus T5. So T4 minus T5s. So in an ideal case we will have T4 minus T5s, but in actual we have only T4 by T5. So this we can substitute the values. T4 is known as 1200 Kelvin, minus T5 is what we need to find, and on the denominator we have 1200 minus T5 is, that is 662.45. So T5 can be calculated as 1200 minus 0.86 of 1200 minus 662.45. Can you calculate T5?
So T5 is 737.707 Kelvin.
Okay, 737.7 Kelvin. And so now we have effectiveness. Effectiveness is T5 minus T6 by T5 minus T2. So here only T6 is unknown, and effectiveness is 0.72. 0.72 is 737.7 minus T6 divided by 737.7 minus T2 is given as 580 Kelvin. So here this is the heat transfer, right? Heat transfer is T5 minus T6. This is actual heat transfer, and that is what we need to find. So we can directly write this as heat transfer, and then heat transfer will be 0.72 times of 737.7 minus 580. Can you calculate the heat transfer?
Sir, 113.54.
This is in kilojoules. Okay, sorry, I think this is just a temperature difference delta T, and for delta T is 113.54, and for heat transfer we need to have Cp mCp into dt. Is there some mCp? There's no. So Cp into delta T, that is Cp is 1.005 into 113.54. Can you calculate heat transfer?
Sir, 114.11.
1 kilojoule per kilogram. So here it's given 152 when they have considered a variable specific heat, but we have considered a constant, so we have got a different value. It's alright. So now we can calculate the thermal efficiency. So for thermal efficiency we need work output Wt minus Wc divided by Qin, and that is enthalpy H4 minus H5, and minus this is H2 minus H1 divided by Qin is H4 minus H3. H4 minus H3. So writing everything in terms of temperature, the overall efficiency will be T4 minus T5 minus T2 plus T1 divided by T4 minus T3. Do we have all these temperatures? T5 we have, T4
Sir, we don't have T3, sir.
T3 okay. Okay, then we can find out that. So with the heat exchanger, heat transfer is H5 minus H6. So that is the heat transferred by the hot fluid is gained by the enthalpy gained by the cold fluid as well. So that is H3 minus H2. So now we can write everything in terms of temperature, that is T5 minus T6 is equal to T3 minus T2. So T3 is T5 minus T6 plus T2. T5 is 737.7 minus T6 is, so here we have T5 minus T6 directly, so we can write that. So that is 113.54. I think T5 we will need it anyway. I think it's better we find T5. Oh, sorry, T5 is not. Okay, fine. So plus T2. T2 is 580, right? T2 is 580. Can you calculate T3?
Six nine three point five four, sir.
So efficiency of the turbine is T4 is 1200 minus T5 is 737.7 minus T2 is 580 plus T1 is 290, so 300 divided by the T4 minus T3. T4 is again given, that is 1200 minus T3 is 693.5. Can you calculate efficiency?
The 0.82.
0.82. That is very high.
Yes, sir.
Sir, my answer is becoming 0.35.
Okay. Yeah, I'm also getting 0.36.
Yes, sir, 0.35, 0.9, so it means
Yeah,
sir,
yeah.
point.
Hmm. That is what we have here also. Can you check the other person?
Yes, sir, I'm doing again.
Yeah.
Yes, sir, 0.35.
Yeah. Okay. Do you have any questions? We can go to the next problem.
No, sir.
So the next problem, we have an ideal air cycle consists of an isentropic compression, constant volume, heat addition, heat transfer, isothermal expansion to the original pressure, and constant pressure heat transfer to the original temperature. Deduce an expression for cycle efficiency in terms of volumetric compression ratio Rk and isothermal expansion ratio Re. In such a cycle, the pressure and temperature at start of the compression are 1 bar and 40 degrees Celsius. The compression ratio is 8 and the maximum pressure is 100 bar. Determine the cycle efficiency and the MEP. So to draw in a PV diagram, first it is compressed isentropic. So we have say something like this from 1 to 2, and then an isothermal constant volume heat transfer. So that would be like this. From 2 to 3, somewhere it is 3 and some negative 4. And then isothermal expansion to temperature to the original pressure. So that means original pressure is here. There is an isothermal expansion like this. And that is from 4 to 5. That is the expression for the cycle. So we can just keep calculating the temperature at different points and then uh, calculate the efficiency in total. So expression for the cycle efficiency. So cycle efficiency, sorry, eta cycle will be work net work divided by Qin. Net work will be W turbine minus W compression divided by Qin is Now we can calculate these things separately and then finally bring it here. Compression work can be written as compression work can be given by Cp into T2 minus T1, and here T2 is T1 into compression ratio power gamma minus 1. So WC is Cp into T1 into T Cp into T1 Cr power gamma minus 1 minus T1. So this can be written as Cp into T1 into compression ratio power gamma minus 1 minus 1. This is compressor work, and similarly turbine work can be calculated. So for turbine work, we have Cp into T4 minus T5. Cp into T4 minus T5. But they said it is constant temperature isothermal expansion, so we cannot write it this way. If you see in TS diagram, 1 to 2 will be like this, 1 to 2, and 2 to 3, 2, 3, 4 are constant volume iteration, so it will go somewhere like this. So it will be 3 and it will be 4. And then we have isothermal expansion to the same pressure. So say this pressure goes like this, it is expanded like this, right? So what is the work done in isothermal process? Work done in isothermal process. So if we write pressure PV equal to T, so here temperature is constant, that means P is inversely proportional to volume. Now then we will have dV by V. So work done is ln of V. think it is getting time. You can also try this at your end, and we can solve this in the next class. Do you have any questions?
No, sir.
Okay, then we will see you in the next class. Thank you for participating.